Hello, AP Calculus. I've got a new video for you. All right, so we talked about the first and second derivative tests pretty extensively before Thanksgiving break and then the past 2 days now. I'm going to talk to you guys about how you can use some of the similar concepts from those two derivative tests to find the actual maximum and minimum values over a specified interval. So some textbooks will call it absolute max and min. Some of them will just call it max and min and leave off the relative part. So the first one I'm going to talk about is number 2. So when you look at 8x minus x squared, some things should pop out at you right away. You should be thinking, hey, this is a parabola. Not only is it a parabola, but it's an upside down parabola because the x squared, the leading coefficient, is negative. Looks something like this. So the question is this relative max that you see right here going to be in between 0 and 6? So just thinking right off the top of your head, you should be thinking, all right, if this is in between 0 and 6, then my relative max is my absolute max. But to kind of sidestep this whole graphing and analytical approach, what we can do is use derivatives. We take the derivative, and we get 8 minus 2x. So the critical number should be 1 point to consider for the absolute max or min value. So the critical numbers, which are always the zeros of the derivative, I guess the critical numbers that aren't points of non-differentiability or domain issues. The critical numbers, which is the solution to this equation, it ends up being x equals 4, should be considered / tested as absolute min / max candidates. So a lot of times in textbooks, what you'll see is somebody will put like an XY table, seemingly randomly, where they'll say, consider these x's. Now plug them into f of x. And that's really exactly what you're doing here. So the first consideration is going to be x equals 4. What value does x equals 4 give you? Well, when you plug it in up here, you get 8 times 4, which is 32, minus 4 squared, which is 16. 32 minus 16 is 16. All right, good to know so far. Since x equals 4 is in between 0 to 6, then it is a quality candidate for this. But here's the second thing we should also consider. Not just the relative max or min, we must also consider / test the endpoint values. As possible absolute max min values. Because as you can see here, clearly one of the endpoints is going to be the minimum value. It's otherwise impossible to determine that. So what are the two endpoints? X equals 0 and x equals 6. So we're going to consider x equals 0 and consider x equals 6. When you plug in 0, you get 0 minus 0. When you plug in 6, you get 48 minus 36. 48 minus 36 is 12. So here's what this information, all of this amounts to. We've got a maximum, an absolute maximum value of 16 at x equals 4. We've an absolute max because it's the largest number that came out of this. I'm sure you guys can't see all of that. There you go. And we've an absolute min And you know what? I should say we have an absolute max of 16 at x equals 4. Because a lot of times the absolute max itself is defined as the y value. It's the highest point. And when you talk about highness, you're talking about verticality, the y-axis. So y values for how high it is. And our absolute min is 0 at x equals 0. And this answers the question. So in a nutshell, in summary, when we're trying to determine through calculus means what the absolute max or min is, you just test the endpoints by plugging it into the original and test the critical numbers, the zeros of the first derivative, by plugging those into the original as well. And you just got to make sure your critical numbers are in between the two domain values right there. So let's do one more where you have to maybe do a little bit more aggressive derivatives. And then I'm going to show you guys what to do when you don't have actual endpoints, but like say it's negative infinity to infinity or 0 to infinity, something kind of funky like that. But number 6 first. So take the first derivative of that. Looks like we need to do product rule if we move the x squared plus 2 to the top and give it a negative power. I think I'm just going to stick with quotient on this one. So f prime, remember it with me, it's the bottom times the derivative of the top minus the top times the derivative of the bottom, which is 2x, all divided by the bottom squared. All right, distribute the 1, you get x squared plus 2 minus 2x squared, all over the same thing. So our first derivative amounts to negative 1x squared plus 2. Now your job is to set it equal to 0 and find what are we talking about? The solutions to it, right? 0 equals, and you know what? When you set a fraction like this equal to 0, the top is the only thing that yields the actual zeros of the function. The bottom gives us domain issues. The bottom critical numbers do not matter right now because that would be the place where the function doesn't even have existence. It doesn't exist at the bottom equaling 0. By the way, the bottom equaling 0 can't happen because the inside's positive. Square something, it's positive. Add 2 to it, it's positive. So it's kind of hard for that to equal 0 at any point. At any rate, this is the only logical critical number that you need to actually do. Set the top equal to 0. When you solve it, add 1x squared to both sides, square root it. You get plus or minus root 2. So you ask yourself, are those legitimate candidates, each of them, based on the, what are we talking about? The interval given in which the function even exists. Well, negative root 2 is negative 1.414-ish. That's out of bounds. So you don't have to consider the negative root 2. We just got to consider positive root 2 and the endpoints. Negative 1 and 4. By the way, a lot of times on the AP test, they'll be looking for this to just give you points. They'll be like, did they consider the critical numbers and the endpoints? You say, yes, we did. And they're like, I'm going to give you some points. So plug root 2 into the original. What is root 2 divided by root 2 squared plus 2? Well, root 2 squared plus 2 on the bottom is 4. It's root 2 over 4. which approximately, it's less than half, right? 2 over 4 is a half, so root 2 over 4 is something less than a half. We can get out the calculator if we need to, but for now, let's just figure out what the fractions are. So negative 1 squared is 1, plus 2 is 3, negative 1/3 is this one right here, and then when you plug in 4 over 4 squared plus 2, that gives you 4 over 16 plus 2. 16 plus 2 is 18. 4 over 18 is 2/9. So this is 0.2 repeating, this is negative 0.3 repeating, and this one, I'm not exactly sure. If I had to take a guess though, where's my calculator? If I had to take a guess, I'd probably say it's somewhere around, let's see, 1.4, that'd be 0.7, probably 0.35. Root 2 divided by 4 is 0.354. So, what is the absolute max? The absolute max is root 2 over 4 at x equals positive root 2. What's the absolute min? Is negative 1/3 at x equals negative 1. All right, so the question is, do I show you guys some trig? Why not? Let's check out number 11. Or did I assign number 11? I'm not sure. I'll do number 11. No, I want to see for sure. No, I'd have to stop the video because, never mind. I'm going to do number 11. Two secant of x minus tan x. And we're going from 0 to pi over 4. Well, we know right off the bat we're going to have to consider 0 and pi over 4. So if you like going out of order a little bit, you can test those points right away. You can say, consider x equals 0. Secant of 0 is... What is secant of 0? Here's 0. That's 1, 0. Secant is 1 over cosine. So cosine would be 1 in this case. 1 over 1 is 1. So it'd be 2 times 1 minus, what's the tan of 0? Well, tan is sine over cosine, so it'd be 0. It'd be 2. Okay. Pi over 4? What is pi over 4? 2 secant of pi over 4 minus tan of pi over 4. If you recall, this is the one that's the 45-degree angle, which means tan's going to be opposite over adjacent, same values. So it's going to be 1 right here. Secant of pi over 4 ends up being root 2 over 1. So this is going to be 2 root 2 minus 1. So right now, who's got the lead? 2 times 1.4. I think this one's got the lead for biggest value. At any rate, to check out our other candidates, we are going to take the derivative. So if you recall, the derivative of secant is secant tangent. And then the derivative of tangent is secant squared. All right, set that equal to 0. Oh boy. We're getting some trig flashbacks here. Not a problem. We know what to do. You see secant of x for both of them? Factor it out. You get 2 tangent of x minus secant of x, which means we've got the zero product property. We can set this equal to 0, which, by the way, that has no solution. Secant can't equal 0. Secant equals 0. Get it? Yes. All right, it's been a long day. Forgive me. All right, and what are we supposed to do with this situation? Well, we could turn them both into sines and cosines. That might work. Or, if you recall, there is a Pythagorean identity that unites secant squared with tangent squared. So if we can somehow get these to both be squares, then we're in business. Let's square both sides. And then you've got a couple options at this point. We can use a paidenity to convert one to the other and then solve from there. I'm going to go with turning secant squared into 1 plus tan squared. So the actual paidenity is 1 plus tan squared equals secant squared. By the way, here's how you can figure that out. You take your original paidenity, which is cosine squared plus sine squared equals 1. And you just ask yourself, okay, how do I create tangent? Well, you just divide everybody by cosine squared. Interesting. So you really only have to memorize one of them. So then these can come together. Take away 1 tan squared. You get 3 tan squared equals 1. Divide by 3. Square root both sides. That's going to be root 1 over root 3, which is the same as root 3 over 3. If you recall, tangent equals root 3 over root 3 at all the pi over 6's. So 5, 7, 11. And then you got to ask yourself, did squaring this fundamentally change it in such a way that we've got some extraneous solutions? So you plug back into the original just to check them out. And when you do that, I believe you get... two of these probably don't work. Well, actually, by the way, we're in between 0 and pi over 4, right? Not in between 0 and pi over 4. Not in between 0 and pi over 4. Not in between 0 and pi over 4. This is our only candidate, potentially. So what happens when you plug it in? Well, I could use my calculator, and since this video is pushing 19 minutes, I should probably just do that really quick. So 2 times, and if you're using a calculator, you can put 1 divided by the cosine of whatever you're doing. Make sure you're in radian mode always. Well, not always, but, you know. 2 times 1 over cosine of pi over 6 minus the tangent of pi divided by 6. I got 1.732, which is root 3. So I got root 3, which is approximately 1.732. The question is this bigger than that? And the answer is for sure, definitely. This is the min, and this is the max. And if you just wanted to confirm it, it's going to be like 0.8 or something like that. 2 root 2 minus 1 is No! Oh, I can't believe it. I made a mistake. Okay, I can believe it because I've made many mistakes. This actually ends up being approximately 1.828. I don't know what I was thinking there. I wasn't thinking. That's the min. All right, 20-minute video. I'm going to cut her off here. And, wow. Yeah, I'm just going to...